Welcome to World Decoder, where we unravel the complex machinery that powers our modern civilization and shapes our future reality. Look around you right now. From the smartphone in your hand to the cars driving past, silicon chips control everything. These tiny silicon brains process billions of instructions every single second, making our connected lives and global economy possible today. But have you ever stopped to wonder how we actually build these incredibly complex structures at such a microscopic scale? For decades, we have followed a prediction known as Moore's Law, doubling the number of transistors on a chip regularly. We went from components that were visible to the naked eye to switches that are smaller than a strand of DNA. But around the year 2015, the entire semiconductor industry was about to crash into a fundamental physical wall. The problem was light itself. We had reached a point where our tools were too blunt to carve smaller details. Imagine trying to write your signature on a grain of rice using a thick marker pen. It is simply impossible. When the wavelength of light is larger than the pattern you want to print, the image becomes a useless blur. To continue the digital revolution, we needed a new kind of light with a wavelength shorter than ever seen before. Enter extreme ultraviolet, or EUV. This was the holy grail that promised to save Moore's Law from becoming ancient history. Previous machines used deep ultraviolet light at 193 nanometers. EUV slashed that number down to a tiny 13.5 nanometers. This wavelength is so incredibly small that it allows us to print features that are literally just a few atoms wide. But generating this light and controlling it turned out to be the hardest engineering challenge humans have ever faced. The first problem is that extreme ultraviolet light is absorbed by absolutely everything, including the very air we breathe. This means the entire process must happen inside a perfect vacuum, creating an environment similar to the emptiness of outer space. You cannot use lenses to focus this light because glass also absorbs it. Conventional optics became completely useless for this machine. Instead of lenses, engineers had to design a system of mirrors to bounce the light to exactly where it was needed. One company in the Netherlands, ASML, decided to take on this impossible mission when everyone else had given up hope. ASML was not a household name, but they quietly became the most important technology company that the world has ever known. Inside their clean rooms, thousands of brilliant minds worked to solve physics problems that should have been impossible to overcome. A single speck of dust in this environment would be like a boulder crushing a city, destroying the delicate circuitry instantly. The machine they built is the size of a bus and contains over 100,000 of the most complex components. Shipping just one of these machines requires multiple cargo planes and months of careful installation and calibration at the factory. The development cost was astronomical, requiring investment that exceeded the budget of many small nations combined over several decades. It was so expensive that competitors Intel, Samsung, and TSMC had to pool their money to help ASML finish the development. But the biggest challenge remained. How do you generate enough extreme ultraviolet light to make the manufacturing process economically viable? You cannot just buy a light bulb for this. You need to recreate conditions that only exist in the most extreme stars. The solution scientists found involves the metal tin. When heated to extreme temperatures, tin emits the specific wavelength we need. Inside the machine, a generator shoots droplets of molten tin across a vacuum chamber at speeds of hundreds of miles per hour. Then, a high-powered carbon dioxide laser is fired. This is not a simple laser, but a weapon-grade beam of pure energy. The laser must hit the moving droplet of tin. This has been compared to hitting a golf ball with an arrow, but it is even harder than that. Imagine the golf ball is moving at supersonic speeds, and you are shooting from miles away. To make it work, they don't just hit it once. Two powerful laser pulses strike every single droplet. The first pulse is a pre-pulse. It does not vaporize the tin, but flattens it into a pancake shape. This shape provides a larger target for the main laser pulse, which follows nanoseconds later with devastating power. The tin is instantly vaporized into plasma, reaching temperatures of hundreds of thousands of degrees, hotter than the sun's surface. This superheated plasma emits the precious extreme ultraviolet light that we need to print our microchips. This incredible process does not happen once. It happens 50,000 times every single second, continuously, for weeks on end. The engineering precision required here is like hitting that golf ball during a hurricane while riding a roller coaster. To catch this light, a special collector mirror is placed near the plasma. This mirror must survive the violent explosion. The plasma explosion creates debris that would normally destroy any mirror instantly. ASML had to invent a way to protect it. They use a continuous flow of hydrogen gas to guide the debris away, keeping the precious mirror clean and functional. Once collected, the light is guided through a complex optical train, bouncing off multiple mirrors to refine the beam. These are not ordinary mirrors. They are manufactured by Zeiss in Germany, the world leaders in precision optics. Normal mirrors absorb EUV light. These mirrors are made of alternating layers of silicon and molybdenum to reflect the specific wavelength. The flatness of these mirrors is mind-boggling. They are the smoothest surfaces ever created by human hands in history. If you scaled one of these mirrors up to the size of the entire country of Germany, it would be incredibly flat. On that country-sized mirror, the highest bump would be less than 1 millimeter tall. That is the precision we are talking about. These heavy mirrors must also move with incredible speed and acceleration to scan the light across the silicon wafer. They are suspended by magnetic fields, floating in the vacuum, reacting instantly to adjust the light path with nanometer precision. The light bounces off a mask, which holds the blueprints of the chip design, before being shrunk down onto the wafer. Finally, the light strikes the silicon wafer, which is coated with light-sensitive chemicals, etching the pattern into the material. The wafer stage accelerates faster than a fighter jet, stops instantly, prints, and moves again, thousands of times per hour. Sensors measure the position of the wafer millions of times a second, correcting for even the slightest vibration or temperature change. The accuracy required is equivalent to shining a laser pointer from the moon and hitting a specific coin on Earth. Other optical giants like Nikon and Canon tried to develop this technology, but eventually gave up due to the immense difficulty. ASML became the only company in the world capable of building these machines, giving them a total monopoly on the future. This monopoly has made ASML a focal point of global geopolitics, as nations compete to secure their supply of advanced chips. Walking through the ASML factory feels like stepping into a science fiction movie where the future is being built today. A single high-NA EUV machine costs over $350 million, making it the most expensive tool ever made. Yet, for chip manufacturers, these machines are a bargain because they are the only way to print the chips we need. It wasn't always like this. In the early days, ASML was a small joint venture struggling to survive in a leaky building. When EUV was first proposed, most scientists laughed. They said the engineering challenges were too great to ever be solved commercially. George Bernard Shaw once said that all progress depends on the unreasonable man. The engineers at ASML were certainly unreasonable. They faced decade after decade of failure. Prototypes didn't work, power levels were too low, and budgets were constantly overrun. But they refused to give up. They kept iterating, solving one impossible problem after another, driven by a vision of the future. This machine is not just a Dutch achievement. It represents the pinnacle of global collaboration across America, Germany, and Japan. Now, ASML is launching the next generation, high numerical aperture EUV, which will allow us to print even smaller features. These new machines use larger, more complex mirrors to capture light at wider angles, pushing the limits of physics further. This technology paves the way for 2 nanometer chips and beyond, ensuring computing power continues to grow for years to come. These chips will power the artificial intelligence revolution, enabling computers to solve problems that are currently beyond our comprehension. They will revolutionize medicine, allowing us to simulate complex biological systems and design new drugs to cure diseases faster. Advanced computing helps us model climate change and develop cleaner energy solutions to protect our planet for future generations. When you look at this machine, you are looking at the most complex object ever mass-produced by the human race. It is the perfect marriage of theoretical physics and heavy industrial engineering, a testament to what we can achieve together. Behind the cold metal and lasers are thousands of passionate people who dedicated their lives to pushing the boundaries of possibility. The story of EUV lithography teaches us that physical limits are often just engineering challenges waiting for a creative solution. If you are fascinated by how the world works, there is so much more to discover beneath the surface of everyday things. From a droplet of tin to a flash of plasma, from a perfect mirror to a silicon chip, the process is miraculous. So the next time you use your phone, remember the incredible journey of light that made that device in your pocket possible. We hope you enjoyed this deep dive into the world's most important machine. It is truly a marvel of our time. If you want to understand more about the technology shaping our world, check out our other documentaries on this channel. Technology is moving faster than ever, and we are here to help you decode the complexities of the modern age. What other engineering marvels do you think deserve a spotlight? Let us know in the comments below. We love hearing from you. Don't forget to like and subscribe to World Decoder to never miss an episode of our scientific explorations. Thank you for watching, and keep asking questions about the world around you. See you in the next video. This documentary was researched and produced by the World Decoder team, dedicated to bringing you high-quality educational content. Stay tuned for our upcoming series where we will tackle the mysteries of quantum computing and the promise of fusion energy. World Decoder, decoding the universe, one story at a time. Goodbye for now. Let's take a moment to appreciate the vacuum system. It must maintain ultra-low pressure while massive amounts of gas are injected. Even with hydrogen flow, mirrors eventually get dirty. ASML developed a way to clean them with atomic hydrogen without opening the machine. These machines are energy hungry. A single EUV tool consumes 10 times more power than previous generations of lithography scanners. The tin used in the process is not wasted. A complex system collects the vaporized metal and recycles it for reuse. Operating these machines requires specialized training. ASML runs an academy to teach engineers how to handle this alien technology. Maintenance is a major operation. When a machine goes down, it costs the chip factory millions of dollars every hour. The EUV light is dangerous ionizing radiation. The machine is heavily shielded to ensure the safety of everyone working nearby. Governments around the world are now racing to build their own semiconductor ecosystems, realizing that chips are critical national infrastructure. TSMC in Taiwan owns the most EUV machines, making them the manufacturing hub of the world's most advanced digital logic. Samsung and Intel are also pushing the boundaries, using high-end AEUV to regain leadership in the relentless race for performance. In the future, we might move beyond silicon to new materials, but lithography will likely remain the key manufacturing method. Quantum computing requires different structures, but the precision engineering pioneered by ASML will still play a crucial role in building them. The global digital economy, worth trillions of dollars, rests on the foundation of these machines continuing to work perfectly. The pandemic showed us how fragile supply chains are. A shortage of chips stopped car factories and delayed electronics worldwide. By 2030, the demand for computing power will explode. ASML is already designing the machines needed for that era. Every amazing photo you take with your phone is processed by neural networks on chips made by these very machines. The realistic graphics in modern video games are only possible because we can pack billions of transistors onto a graphics card. High-speed 5G and future 6G networks rely on advanced radio frequency chips manufactured using this extreme ultraviolet technology. Space exploration depends on powerful, energy-efficient chips to allow rovers and probes to think and navigate autonomously on distant planets. It is a triumph of mathematics. Every movement, every laser pulse, every mirror angle is calculated with mathematical perfection. The air in the ASML cleanroom is thousands of times cleaner than the air in a hospital operating theater. Moving the machine is a logistical nightmare. The trucks must drive slowly and smoothly to avoid damaging the sensitive components. Once it arrives, teams of engineers spend months assembling and calibrating the machine before it can print a single chip. Quality control is obsessive. Every wafer is inspected and any defect is analyzed to prevent it from happening again. Semiconductor fabrication uses massive amounts of water, so advanced recycling systems are essential to minimize the environmental impact. The industry is also striving for sustainability, using renewable energy to power these energy-intensive manufacturing processes. While the hardware is proprietary, the software running on these chips often comes from a global community of open-source developers. Security is built directly into the silicon. Modern chips have dedicated areas to store passwords and encryption keys safely. It's not just logic chips. Memory storage has also benefited, stacking cells vertically to store terabytes of data. ASML continues to innovate. They are already working on technologies for the 2030s, staying 10 years ahead of everyone else. Ultimately, this technology is about connection. It allows us to communicate, share ideas, and work together regardless of distance. It democratizes education, giving a child in a remote village access to the same information as a student at Harvard. It powers our entertainment, delivering high-definition movies and music from the cloud to our devices instantly. It drives global commerce, managing complex logistics networks that deliver products to your doorstep the very next day. It runs the financial system, processing billions of transactions securely and enabling the global flow of capital. It enables new technologies like blockchain, creating decentralized systems for trust and verification without intermediaries. It opens the door to virtual reality, creating immersive digital worlds where we can play, learn, and socialize. Augmented reality will overlay digital information onto the physical world, changing how we navigate and interact with our surroundings. Autonomous vehicles will make transportation safer and more efficient, powered by supercomputers on wheels processing sensor data. In the future, robots might help us with daily chores, caring for the elderly, and giving us more free time. Smart farming uses sensors and drones to optimize crop yield, helping to feed a growing global population sustainably. Smart cities will use data to optimize traffic, reduce energy consumption, and improve the quality of life for residents. Networks of sensors protect our environment, detecting forest fires early and monitoring pollution levels in our cities. We are exploring the depths of the ocean with autonomous submersibles, discovering new species and resources. We are seeing a convergence of biotechnology, information technology, and nanotechnology, leading to breakthroughs we cannot yet imagine. As chips become more powerful, we must also consider the ethical implications of artificial intelligence and automation. Protecting our privacy in a digital world is a challenge that requires both advanced technology and wise legislation. We must ensure that the benefits of this technology are shared equally, bridging the digital divide between nations. We are the architects of the future. The tools we build today will shape the lives of generations to come. We hope to inspire the next generation of scientists and engineers to dream big and solve the world's hardest problems. Curiosity is the engine of progress. Never stop asking how things work and why they are the way they are. ASML's story is a reminder that with enough persistence and collaboration, even the most impossible challenges can be overcome. There is a profound beauty in engineering. It is the practical application of our understanding of the universe. We stand on the shoulders of giants. Every breakthrough today is built upon centuries of scientific discovery. The future is not yet written. It is being built right now in labs and factories around the world. Join the conversation. Tell us how technology has changed your life and what you hope to see in the future. As we conclude this journey, let the magnitude of human achievements sink in. We have truly decoded a piece of the world. World Decoder is committed to bringing you the best stories from the frontier of science and technology. Thank you for watching World Decoder. Subscribe now and join us next time as we continue to explore the impossible.